Welcome everyone to our channel Mathematics Parshala. This is a problem of CSIR UGC NET June 2023 Mathematical Science. This is a problem of abstract algebra, ring theory. See the question here. Which of the following are maximal ideals of ZX? So this is a question of polynomial ring. ZX is a polynomial ring. Now we have to check which one of these four ideals are the maximal ideals in ZX. So see option 1, the ideal is generated by 2 and 1 plus x square. So this is not a principal ideal. So this is not a easy work to see easily that it is a maximal ideal or not. So for this, let us first prove a theorem, that is, see here, the quotient ring ZX by an ideal generated by P comma Fx, where P is a prime element in ZX, is isomorphic to the quotient ring ZPX. ZP is a field. Since P is prime, ZP is a field. So ZPX by the ideal generated by Fx. So if we can prove this result, then very easily we can conclude that out of these four options, which one will be maximal and which one will be not. So see, first, to prove this theorem, we use a function phi from the ring ZX to ring ZPX by this ideal generated by Fx. So we define this map by phi of gx. If we take gx a polynomial in zx, then phi of gx is defined by gx class modulo p plus the ideal generated by fx. So the right one is codomain is quotient ring. So any element of this ring will be of the form some polynomial in zpx plus this ideal. So how it is defined? Phi gx, if we take gx belongs to zx, then phi gx is gx class plus fx. This class gx is obtained from gx by congruent modulo p. That means taking remainder of each coefficient when that is divided by p. So now it is an easy exercise to see that this map is well defined, because if we take any two polynomial gx and hx such that they are same, we have to show that their image is also same. So very easy to see that if the two polynomials are same, then their class gx equal to class hx. We just denote this class gx by that polynomial which is taken from gx by congruent modulo p. So this will be happen, and then also this class gx minus class hx, as this is same, this will be 0 and this will be in this ideal generated by fx. So we will have this class gx plus fx equal to this class hx plus this fx. That means this is our phi gx and this is our phi hx. So this proves that phi is well defined, and now it will be also can be proved very easily that if we take two element gx and hx belongs to zx, then just verify by yourself that phi gx plus hx, this will be actually our gx plus hx class plus ideal generated by fx, and then this gx plus hx class will be also equal to class gx plus class hx. So like this, a plus b plus I equal to a plus I plus b plus I. This a plus b plus I, the definition of this uh, sum in quotient ring will be a plus I plus b plus I, and also for the product ab plus I equal to a plus I into b plus I. Using that, these two will be done. So this will be phi gx plus phi hx, and also another that a plus ab plus I, that ab plus I will be equal to a plus I into b plus I. Using that, it can be proved also that phi gx hx equal to phi gx into phi hx. So phi will be a ring homomorphism. Phi will be a ring homomorphism. Now also this is very easy to see that phi is onto. So phi is a onto ring homomorphism from this zx to this zpx by fx, ideal generated by fx. So now we are going to use the first isomorphism theorem for this ring. So the theorem is if phi is a ring from R to R dash, phi is a ring homomorphism from the ring R to ring R dash, which is onto, then first isomorphism theorem says that this R by car phi quotient ring is isomorphic to R dash. So we will use this result here. So here our zx, R is there zx by car phi is will be isomorphic to the ring which is our codomain, which is zpx by the ideal generated by fx. So to get the required result, we only need to show that car phi is actually the ideal generated by this p comma fx. So if we can prove this car phi equal to this, then our required result will be proved. So now let us see which is our what is our car phi here. Just let me write the car phi. Car phi equal to all such element gx belongs to zx such that the image of this phi gx will be the identity element in zpx by ideal generated by fx. So in this ring the identity element is this ideal generated by fx. So let me again write this. All such gx belongs to zx such that the definition of phi is this plus gx, which is taken from gx by congruent modulo p plus this ideal generated by fx equal to the ideal generated by fx. So this is a easy result that a plus I equal to I if and only if a belongs to I. So this is actually plus gx belongs to this ideal generated by fx. So that means all such gx belongs to zx such that this class gx will be of the form some multiple of fx. So fx into say another polynomial in zx, say psi x. So now if we take any polynomial gx from zx, then zx is of the form a0 plus a1x plus a2x square up to say an x to the power n. And see, we can write this polynomial in this way that p into some coefficient b0 plus say A0 class plus PB1 plus A1 class X plus PBN plus class N x to the power N. How we can write this? Just take, if we divide this A0 by P, then we get a quotient say B0 and a remainder say R0. So then we will have this A0 equal to P B0 plus R0, and we are writing this R0 by class A0, thus denote this R0 by remainder, denote this by class A0. So this is, in this way, all such AI, we are writing this AI equal to P into Bi plus class AI, this, in this way. So now this equal to, we have, so this, from this we will have, this is P into some this B0 plus B1x up to Bn x to the power n plus this class A0 plus class A1x up to class An x to the power n. So now this is our P into some polynomial say hx plus this is a polynomial actually class gx, because this polynomial is obtained from gx by congruent modulo p. So now if we take any gx, let any gx belongs to car phi, then we have to see the structure of this gx. So then this gx is actually our this polynomial what we get just now, p into hx plus gx class, and this is, since this gx belongs to car phi, also we have that this class gx will be of this form, some multiple of fx, so fx into say psi x. So clearly this belongs to this ideal which is generated by p into fx. And also from this we have this car phi is subset of this ideal generated by p into fx. And also the converse part is very easy, because if we take any hx belongs to this ideal p into fx, then our this hx will be of the form, this hx will be of the form p into some polynomial say phi 1x and fx into another polynomial say phi 2x. Then our phi of hx will be phi of these things. Since phi is a ring homomorphism, we have phi of p into phi 1x plus phi of this fx into p phi 2x, phi 2x. So now our the definition of phi, this is also our 0, that is here 0 plus that ideal generated by fx, and also this is, since belongs to this ideal generated by fx, so this will be also ideal generated by fx. So this is actually our equal to this ideal generated by fx, that means the identity element in the codomain. So this hx, so this hx belongs to our car phi. So now we have this car phi equal to this ideal. So what we have, car phi equal to the ideal generated by p and fx. So by first isomorphism theorem, we now have this zx by car phi, that means this ideal p comma fx is isomorphic to this zpx by ideal generated by fx. So this result is a very important result and we will use this result to solve this problem. So now see, look at our option 1, 2, 3, 4. See here, for option 1, we have this ideal zx. We have zx by this 2 comma 1 plus x square. This ideal, this ring is isomorphic to by this result z2x by ideal generated by 1 plus x square. So now this is very easy to see that z2 is field and z2x is PID, in fact Euclidean domain. So here it's easy to see that this 1 plus x square is actually uh, reducible because 1 is a root of this polynomial. If we take gx equal to this polynomial, then g1 equal to 0, that means g class 1 equal to 0. So this polynomial has a root in z2. So we know that a polynomial of degree 2 or 3 over a field is irreducible if and only if it does not have a root in this field. So this polynomial has a root in z2, so this is not irreducible. So since this is not irreducible, so this polynomial this ideal 1 plus x square generated by this ideal is not the maximal ideal. Is not the maximal ideal among the collection of all principal ideals, but since this z2x is PID, all ideals are principal ideals. So in fact this ideal is not a maximal ideal. So since this ideal is not a maximal ideal, in z2x, so this is not a field because we know that R by I is a field if and only if I is maximal. This is a field. This is a very well known result if and only if I is maximal. So since 1 plus x square, the ideal generated by 1 plus x square is not irreducible. So since 1 plus x square is not irreducible in z2, so in z2x, so 1 plus x, the ideal generated by 1 plus x square is not maximal, and hence this z2x by this ideal is not a field. And since these two rings are isomorphic, so also this ring is not a field. So since this is not a field, by this result also this ideal 2 comma 1 plus x square is not maximal in zx. So this is not a maximal ideal. So this option is not the correct option, and exactly in similar manner we will prove the other options. So for this ideal we have our zx by the ideal generated by 2 comma 1 plus x square is isomorphic to z2x by the ideal generated by 1 plus x square. So for this isomorphism, see, this 1 plus x square, this polynomial is irreducible in Z2 because 0 is not a root of this polynomial and also 1 is not a root. So this polynomial has no root in Z2. So by that theorem, that every degree 2 or degree 3 polynomial over a field is irreducible if and only if it has no root in that field. So it is irreducible in Z2x, and hence this ideal generated by this polynomial is a maximal ideal. So this ring z2x by this ideal is filled, and since these two rings are isomorphic, so this ring this zx by the ideal generated by 2 comma 1 this ideal generated by 2 comma 1 plus x square is a field, and hence this ideal 2 comma 1 plus x square generated by these two elements is a maximal ideal. So this option 2 is the correct option. And exactly in similar manner, first see option 3. Here our polynomial is 1 plus x square, and we have to write this, just let me write 3 and 1 plus x square. So this is our zx by the ideal generated by 3 comma 1 plus x square is isomorphic to, this is for option 3, option 3, z3x by the ideal generated by 1 plus x square. Now also this 1 plus x square has no root in z3, because if we put 0, suppose gx equal to this, so our g0 equal to 1, our g1 equal to 2, our g2 equal to 1 plus 4, 5, that means our 2 also in z3. So this gx, this polynomial is irreducible because it has no root in z3. So this is irreducible in z3x. So this ideal generated by this gx is maximal. This is maximal in z3x, since it is a PID. All ideals are principal ideals, and so this z3x by this ideal generated by this is filled, and since this is isomorphic to this ring, so we have this ring zx by the ideal generated by 2 3 comma 1 plus x square is filled, and hence this ideal generated by this 3 comma 1 plus x square is maximal. So our option maximal in zx. So our option 3 is the correct option. This is the correct option. So for the option 4 again, we are not writing explicitly. We have this zx by that ideal generated by 3 comma 1 plus x square. See here all 2 and 3 are prime in z, so we can use this theorem here. So the ideal, the ring zx by the ideal generated by 3 comma 1 plus x square is isomorphic to z3x by the ideal generated by 1 plus x square. And see, if we take gx equal to this polynomial 1 plus x square, then g1 equal to 3 equal to 0 in z3. So this polynomial has a root in z3, so this is not irreducible in z3x. So this ideal generated by this 1 plus x square is not maximal in z3x, and hence the quotient ring z3x by this ideal generated by 1 plus x square is not a field, and hence the quotient ring zx by the ideal generated by 3 comma 1 plus x square is not a field, and hence the ideal generated by this 3 and 1 plus x square is not maximal in zx. Exactly in similar manner. So here the important thing is this uh, proof of these two rings are quotient ring, then easily we can solve this problem. So this option 4 is not the correct option. So option 1 and option 2 and 3 are the correct options. This is the solution of this problem. Thanks for watching.